Hello, hello. Who am I saying hello to? I can't even see. 1 second. Hello. Who am I saying? Hello. There she is. Hello, Avani. Okay, now the party started. Good morning. Oh, and there's Michelle and there's Melita. Now the part. Hello to you. Nice. Wow. Okay. Whoa. Look at this. Talk about population. Yes. Hello, Avani. Hello, Michelle. Hello, Yavi. Hello, Amanda. Hello, hi, you. Whoa. And wait, whoa. Yeah, see you guys. Telling you what. It's like they're like, I bet he's in a bad mood today. You think we could change it? Yes, you can. I wasn't in a bad. Okay. So Melita, Amanda, Yavi, Marilyn, good afternoon. Matthew, good afternoon. Amanda, double 50. Hi, you. Good afternoon, double. Good afternoon, Freddie. Hello, Avani, double. Good day, Michelle Q. Wait, did she change her avatar? You know, the double means like when it's in video and chat, right? Yeah, okay. Good afternoon, Yayun. Wow. See, like there's literally more video squares than even fit in. I mean, this is like, I swear, like we should monetize. Okay. Wait, I even got a someone even okay, there's Cheska. Did I say Cheska? Hello. I don't know if I don't think I did. Yes, hello. Oh, and by the way, we all know Cheska was in the waiting room like she was early. I'm just saying, like, if this were a doctor's office, she would like her insurance deductibles would have already been processed. Okay, but not in this country. Okay. That is not a political joke. Okay. Good afternoon, everyone. Did I say Yuyun? Good afternoon, Yuyun. It's interesting how Michelle, like, her thing, it changed every day, but in such a subtle way that it's almost like not even clear that it changed, but it did. Okay, I'm stalling. Did I say hello to everybody? Yes, Yavi, Michelle, Amanda, Jessica, Avani. Okay. Not that Chris isn't showing video, or not that anybody notices. I'm going to say, where's Mercedes? Tell Mercedes hello. Okay, no. Um, let's get to it. What I want to get to today. I no, actually, this is a serious question. Uh, lab, lab 5. Have you? This is a real question. Have you done
Yeah,
lab?
we've done it.
You've done it. Thank you, Melita. Okay, and then follow-up question. Did you already turn in the report? Was the report already due, or is the report like not
The
yet?
post lab is due tonight and the formal report next week. And we were talking about what we were learning in class about like the X and Y axis and converting it because like of the tension from the angle of the plane.
First of all, you should submit for 400,000 points for what you just said. Okay. Oh, and Ivani, thank you. I see you in the chat. Okay. No, that's really helpful, Melita. And Melita used her voice, ladies and gentlemen. I mean, not that I'm singling her out, but that was a lot of points. But okay, that is seriously helpful. And great to hear that you were making a cross reference from the lecture. I'm glad that the lecture and the lab are sort of related. And that you're relating them. That's great. And I might even ask more follow-up questions because, okay, so my goal for today, as soon as I get started, you see this picture on the screen right now is totally about your lab. Hopefully some of you recognize. I would like to be able to be helpful since you haven't turned in your formal reports yet, or even the post lab. I would like today to be able to be even more helpful to whatever you're trying to do with your post labs. This is so that's great what Melita just told me and what Avani just wrote. Oh, it's due today. Oh, today, like right after class. Okay. Well, okay. So, I mean, can't promise like that I can fix your problems in time for that, but like, or that you have problems, but certainly for the formal. I want to finish one problem that we were dealing with from the homework yesterday. I'll try to do it quick. And then I want to get to the lab. I have things to say about it, but certainly the priority is to get through this other homework problem. And then what I'm trying to say is, yes, I have things to say about the lab, but the minute we shift gears and we get to talking about the lab, like in 25 minutes, 30 minutes, whatever, then even if I'm saying something, any questions that anybody has that could make their formal report better or make their understanding better, like that should definitely take priority over anything that I'm planning to say. Okay, so I want to do this homework problem first, but absolutely, the goal today is to optimize your understanding and your grade in what's going on in the lab now, because yes, that lab does. Yeah, I mean, I love that lab and it totally does tie in with what we're doing. And so if you've already been trying to make the connections, terrific. Okay, so wait, oh, you have time. Oh, it's due tonight. Okay. Thank you, Vani. Okay, so yeah. So look, let me do this problem just so we're all in the curriculum, but like the more time we can spend on the lab, all the better. And I just do want to know, since that was really helpful what Avani put in the chat and what Melita's saying in life, to clarify, Melita, are you saying that like you guys, like you people, like you friends were talking about the components and stuff like that? Or are you saying that Mercedes was like, are you saying that you people were trying to relate like the lecture material to the lab, or that in lab that actually, or is that a vague question? Well, I'd love to hear more about, well, I guess we'll hear it when we, I mean, you're saying that you guys as peers, as colleagues, were talking amongst each other, or like as lab partners, that you were somehow relating the component stuff from the lecture to what you were working on in the lab. Is that what you're saying, Melita, or anybody? Okay, I'll put, well, maybe she's out for that. All right, we'll get back to that. All right, so so the lab is a main priority for the second half of today. What I want to finish for the first half is that last problem from the homework, from homework 8, problem 5, because I sort of made a little bit of a mess of it. Like I didn't realize to the last minute that the problem actually tells you that the hand is on the right side. So I just want to make this neat and clear. I want to sort of backtrack and give you a neat, clear notes from this problem. So some of it's redundant, so I'll do the redundant stuff fast. Like, so I'm starting the problem over, but I'm just going to like race through the beginning parts. If you have any questions, definitely ask them. But otherwise, I'm going to race because we've said most of it already. So this is, again, problem 5 from homework 8. It's the 2-block situation. The 2 blocks are on a rough surface. And supposedly there's a hand pushing on M2 from the right. So first it asks for a system schema. I think that is the system schema right here on the screen. And specifically, again, remember, at first, the purpose of this problem is really to show us, that a system or a mass to which we're applying Newton's second law, a mass is as big as we want it to be. Whenever you're analyzing a system, no matter how complicated it is, the whole goal in physics is to zoom out as far as you can at first, to collect in your mind as many masses as you can at first, as long as they all have the same acceleration. Like, right? Like, just honestly, just like with the duck, you notice with the duck, we take it for granted we're talking about a duck. Technically, when we're talking about its acceleration and everything, we're talking about at a point at the center of the duck, but we analyze the whole duck. We don't sit there and analyze like a molecule in the duck's spleen or something like that. Like, we are not biologists. We are not chemists. We are physicists. So we look at the biggest mass we can and look at the forces coming from the outside onto that mass. What do I mean by the biggest mass we can? The biggest amount of mass that's all sharing one value of acceleration. Okay, so, and this problem is trying to really emphasize that that's what we do. And once we zoom out and look at something and get its acceleration, then we necessarily automatically have the acceleration of all of its parts, if indeed all the parts were accelerating at the same rate. So then once we've zoomed out on a situation, then we can zoom in and start getting knowledge about internal interactions in that system that we didn't originally have or even like identify. Okay, so that's the thrust of this problem, is that first we're zooming out and treating M1 and M2 together as the system, which we can because of the belief that they are accelerating together. Okay, so that's the system schema for it. I know I said that yesterday, so I'm going to go on. Then that's the pure free body diagram of M1 and M2. We said that yesterday. I'm just reviewing just to get you a clear thing of the notes. So the hand is pulling to the left, the hand is pushing to the left. It's doing so from the right-hand side, but whatever. It's pushing to the left, friction's pushing to the right. Those forces are not equal and opposite. that's why the thing is accelerating to the left. Okay, but the upward and downward forces we think are equal and opposite. Okay, so then in part C, it asks for the normal force exerted up from the table onto this whole system. Tends to be the strategy of solving these problems is that we tend to, whenever possible, we solve for normal force first, which means we tend to analyze the axis along which the normal force is acting first. There's no law that says that that's always the y-axis, but it often is. We analyze the normal force axis first, right? And the purpose for that is that, generally speaking, we need the normal force in order to calculate friction, and that's totally the case in the lab. Or, you know, that they both affect that we do that in the lab. Here, it was more like a warm-up problem assigned a couple of weeks ago. So the friction force was just given to you, which is a little bit artificial and will never happen again. But okay, so here in the y-axis, we say, oh, I guess I skipped a step. Technically, in the y-axis, we say sum of the forces along the y-axis equals the mass times the acceleration of the y-axis. So technically, in the y-axis, it's normal up minus m1, m2g down equals ma, but then we said that along the y-axis a is 0, so that's where we got that. So we brought the m1 m2 g to the other side. That's where we got that statement from. Again, this is all from yesterday, from Monday, but I'm just whatever reviewing it. So the normal force up on the entire system of m1 m2 is 80 newtons. Then we go to the x-axis. We're asked the acceleration of the x-axis, so we say the hand is going one way, the friction's going the other way. Together, they make the acceleration of the horizontal acceleration of the big system. So we did the math. We got 0.75 meters per second squared. In other words, none of this whole time that I was doing this 2 days ago, I was picturing that the hand was on the other side, but that didn't affect any of these answers. But that's what I was picturing because I didn't read the problem carefully enough because I'm a bad person and I should fire myself. But I have tenure, so I'll stop myself from doing that. Okay, so none of these answers were affected, but then we got to E. Okay, E wasn't affected either. It asks, with that acceleration, how far will it go in that amount of time? And the answer is approximately 18.4 meters. Okay, all this was repeated from yesterday. But then we get to part F. Oh, sorry. Oh, thank you, Michelle, for actually answering my question. Okay, sorry, I see 5 minutes later. Thank you, Michelle, for answering that question. Okay, got it. And for always showing video, I might add, duly noted. So F yesterday F is now asking us to zoom in and analyze one of the particular parts of this system. Okay, so this is a little bit interesting now. Like, systems can be analyzed as systems of multiple parts. Again, I'm saying the strategy in physics is you always zoom out. You start at the widest zoom you can and then zoom in. And why? Because by zooming out, we got the acceleration of the whole system. Therefore, necessarily, we got the acceleration of every part of the system because the unifying characteristic of all the parts of the system is acceleration. So now we zoom in and we look at M1 as its own thing. And we draw a free body diagram on M1. And notice it is now a new, different free body diagram. Sure, there's still friction on M1 from the surface. It's less friction than before. And sure, there's still a normal force up on it from the table. It's a lower normal force than before. And sure, it still has weight, less weight than before. But now it has a force on it, which is the force from M2. And I'm calling that force N2 because if you're really following the logic of all this, you'll realize that the force being exerted on M1 from block 2 is a normal force. It's not right. It has nothing to do with gravity. It's not vertical. It's not what, but it's a normal force because there's a surface pushing a surface. So there's a different normal force going to the side on M1. It's the normal force from M2. Again, this was not in the other diagram because the other diagram treated them as one object. But also what's not in this diagram is the hand, because the hand is not directly touching M1. Like I will move on, but I'm literally saying the physics of M1 is different from the physics of the whole situation. What's responsible for the whole situation accelerating left is a hand. What's responsible for M2 moving to the left is not a hand. I'm sorry. What's responsible for M1 moving to the left is not the hand. It's M2. M2 is pushing, just like with the sled. A child may be pulling the string that's attached to the sled, but it's the string that's responsible for the sled's acceleration, not the child. We're only ever dealing with direct contact forces. And I'm even going to throw in one more detail. Like I'm saying, this free body diagram is different. I'm saying the reason that M1 is accelerating is different from the reason for the system's acceleration. And it's not just a different reason, like in English words. We're about to find out that the number is different. Remember, there's a hand pulling on this whole situation, and the hand is exerting a force of 10 newtons. And that's why ultimately the whole situation is moving to the left. We're about to solve for the force acting on M1, and I don't think it's going to be 10 newtons. So, okay, anyway, so, all right, but so there's our diagram for F. And then it asks us to solve, well, for what I just said, for the leftward pointing push onto M1 from M2, i.e., it's asking for the normal force being exerted by M2. So I'm calling it N sub 2. That's what it's asking for. So I just do F net equals MA, like I just apply Newton's second law to M1. I'm solving for, and now I'm using an acceleration to solve for a force rather than the other way around. And how do I know the acceleration of M1? Because it's the same as the acceleration of everything else in this whole system. It's what I solved for a couple of parts ago in the problem, right? It's that 0.75 that I plug in. So I ultimately find by doing Newton's second law onto this part of the system, I find that the normal force exerted on M1 is 3.75 newtons, which is a lot less than 10. So it's like, okay, so that's the answer to that. Again, I'm just looking at chat. Okay, again, the strategy here is you start with a zoom out. You start with the widest zoom. I'm using that as, an expression, and then you zoom in to get internal forces. Again, just know when we started this problem, not only did we not know the magnitude of the force from M2 to M1, but we didn't even identify that it was there. When we're zooming out and treating them as one object, that's not an external force. It's just like acting like glue, holding the objects together. Anyway, all right, so that's the answer. But now the next question, all right, wait, let me say. The next question asks for what is the force exerted by M1 onto M2, right? In other words, well, that's what it asks. Well, it asks for a free body diagram first, which we'll draw. But then the ultimate goal of the next question is to get the other force going the other way. Now, say this were an exam. Whoa, everybody starts paying attention. No, say this were an exam. If you're thinking and you understand what's going on, hopefully it might occur to you that, oh, wait a minute. The force from M1 onto M2 had better be opposite in direction, but equal in magnitude to the force from M2 onto M1. Like that is an action-reaction pair. It's two different objects pushing on each other. That is Newton's third law. So if you were taking an exam right now, you'd be very wise to realize, oh, the question that Yaverbam is asking next, should get the same answer. I agree. No trick. If I were taking an exam, maybe I would write that down. I think this next answer should be the same, or prediction or conjecture. The next answer should be the same because of Newton's third law. But then I would still do it out. Because if this answer is really, this question is really giving you an opportunity to check that your whole method and everything's making sense. Basically what you've just realized, if you realize that this next answer should be the same from Newton's third law, then that means you've realized there's two different ways of getting this next answer. And absolutely, especially because it's an untimed test, you should do both. And if they're both getting you the answer, that makes you all the more confident of what you've done to this point. It's an opera. So what I'm advising is don't just write Newton's third law. They're the same. I'm advising that you don't just do that. I'm also admitting if you did do that, if you wrote Newton's third law, they should both be the same. Would I give you full credit? Yeah, I would. If you're right and if you've done it, I would. But it's a risk on your part because what if you didn't do this part right, or what if you are wrong about that? Anyway, all right. So, and I'd also be that much more excited if I saw someone write that and then do this out and be like, they check. Oh, then I'd be like, well, that person should really, teach physics next year, please, before they go to graduate school. So here I go. I'm going to go to the next one. First, I'm going to draw a free body diagram on the other one. Notice this is a complicated free body diagram. I mean, to be totally blunt, this raised a number of questions in the other section. So feel free, and we still have a ton of time. I'm talking very fast. So if any about what I'm about to do throws you off, don't be ashamed, like ask. What I'm saying here is this is the free body diagram. I'm doing G, right? This is the free body. Yes. Thank you for your honesty. Okay. Yes, I can. Melita, and she went public too, which I totally appreciate. She should give herself 1,000 points. You should use scientific notation for the number of points that you should be submitting for that. And I'm being silly, but I do mean it. Okay. Yes, there's two normal forces in this diagram. The regular N that's pointing up is the normal force you, I think, expect. The normal force up from the table supporting the weight of this object M2. Like this is the free body diagram of M2, okay? But the other one, N sub 1, is going to the right. It's going to the right. Like I know I drew it up there, but it's going to the right. It is the force from M1 pushing on to M2. It says it in bad handwriting up there. It says right. What? I can't even read my own handwriting. It says rightward contact push from M1. Like this whole thing. Now that, okay. And so first of all, forget the fact that it's called N for a minute. I'm just saying there's got to be an arrow somewhere in there that indicates that M1 is in front of M2 shoving against it. Like there's a hand pushing M2 to the left, and that's in the diagram, right? There's a hand pushing M2 to the left. But while M2 is trying to go to the left, it's like jamming into M1. M1 is like slamming up against it to the right. Like that's a force. And in fact, technically, it's a normal force because the surface of M1 is pushing against the surface of M2. They're vertical surfaces. They're like side-to-side surfaces, but that's another reason I'm doing this problem is just like to demonstrate, to show everybody that normal force just means surface pushing against surface. So we've got a normal force coming in from the other block, and I'm calling it N1 because it's coming from mass number 1. I'm going to say one more thing about this, and I'm really going to check in the chat to make sure. I'm glad Melita's asking. I know she's not the only one. Like, she has the guts to raise this. There's no way she's the only one who's slightly concerned about this topic. So I'm not going to go on until I get some kind of assurance from her or other people that like that is clearer now. But the other thing I'm saying is that N1 arrow that's going to the right in this diagram, that is the Newton's third law pair. I mean, that's the reaction to the leftward arrow in this picture. Like, so in fact, maybe technically I should really give them the same name. Maybe that would be less confusing. But this leftward arrow here is M2 pushing against M1. And the thing that Melita's asking about, this rightward arrow up here is the reaction to that. It's M1 pushing against M2. I am now, and the reason I'm excited that she would ask about this, like she's right to ask because it's definitely new information. Like that force was not in our original free body diagram of the whole system. It's definitely something that we're realizing now only because we're zooming in and like focusing our analysis on one piece of the system. When we zoom out and treat it all as one thing, then that is not there. That's like just like glue holding. That would be like putting a subatomic bond or something in our diagram. Like, but when we, in other words, every arrow that you ever put in a free body diagram is supposed to be an external force. and influence from the outside world, from some other object. So we recognize that arrow. Now, only that, we are focusing our entire analysis on M2 as its own object. Now, wait. Okay, so now I'm going to look at the chat. Hold on, did I answer everything I'm trying to say? Right, so this is definitely a complicated free body diagram, and it's more one last thing, and then I'm looking in the chat. It's also more complicated. It's not the mirror image of this diagram. It's not the mirror image because the hand is touching M2, but the hand is not directly touching M1. And again, that's like it's such a subtle point because it's so not subtle. Like, it's just that dumb. Like, the hand is touching M2, so you put it in that picture. The hand is not directly touching M1, so you don't put it in that picture. But what it's surprising to a lot of people because the funny thing about physics is, I'm just gonna say this and then I'm looking at the chat. Remember, one of the reasons that physics is not easy, especially if you've done this much science and this much math and this much work to get yourself to the point where you're in a physics class, one of the reasons physics is not easy is because it is simple and you're not used to simple. Half of you got to this point in your life by mastering the art of overthinking. And physics is actually trying to force us all, including me certainly, trying to force us all to actually back up and underthink. So everybody has a tendency to think like, well, the hand must be doing something to both. I mean, why is the first object going if not because of the hand? The first object is not directly affected by the hand. So the hand is not in the first object's picture. So the two pictures are very different. The second picture is far more complicated. I'm looking in the chat now. Okay, back to Melita. Can you please explain the two ends? So they are both normal forces, but yeah, oh yes, good, Melita. Yeah, they are both normal forces, but they're stemming from different surfaces. Yes, literally different surfaces on different objects. Yes, one of the normal forces is stemming from the surface of the table, and the other one is stemming from the surface of M1. So yeah, they're from different surfaces on different objects, and the two different surfaces are like literally going in different directions on different axes. Absolutely, yes. And then I have a direct chat question, which is a really great question. Someone in direct chat is saying, is it possible to have three normal forces? Yeah, it is. Fair question. In theory, it's possible to have like a million normal forces, but to be more concrete, and this is a classic problem that actually we used to do a lot. All we'd have to do is put a block on top of one of those blocks. If we put a block on top of one of those blocks, then the block in the middle would have a normal up, it would have a normal up from the table. It would have a normal to the side from the other dude, and it would have a normal coming down on it from the block on top of it. That's totally a thing. And then you might even say, well, would you, and we're not doing that here, but you might even say, well, are you just doing that to be like a pain in the butt physics professor? Like, is that even like realistic? Well, totally it is. Like, imagine carrying, if you're a waiter or a waitress and you put things on a tray, like all kinds of things are happening on that tray, especially when you pile them and you start running through the restaurant with a bunch of things on your tray. And absolutely the interactions among the different objects, like the normal forces between the different objects that you've piled on that tray, the normal forces between the objects affect the friction between the objects and affect whether the things stay on the tray or not. So it's like, yes. So the answer is yes. And that's, I'll move on. I will move on. But that's why I'm really trying to emphasize from the start that you don't want to think of like normal just means this. You could have as many of these as you want in a problem, and they could be going in all kinds of directions. And then you just have to solve for them independently. So yes, great question. The person in direct chat believes that he or she is a genius. That doesn't give away at all who it is. Sorry, I shouldn't. Okay. But thank you, Melita. Okay, so that means it was clear to Melita. Great, awesome, great questions. Okay. So we have this complicated free body diagram. And okay, the other thing I'm just trying to emphasize too is like things start looking complicated, right? I mean, they do. I think but it's only getting complicated because we just keep adding elements. Like nothing is out of nowhere. Everything is just building from the same procedure. I don't know if that but like nothing is randomly. Anyway, whatever. We're just doing the same procedure, just adding one element at a time. And sort of all of this is meant to like prepare for the lab thing. Okay, so then I solve for the very force that Melita's asking about. That very force, N1, the rightward pointing normal force acting on M2 exerted by M1. I solve for it by looking at the x-axis where it's asking. So the hand is going to the right. I'm sorry. The hand is going to the left. This whole thing is assuming that left is positive. Why am I making left positive? Because the whole darn thing is accelerating to the left. So I make that positive, and the right is negative. And okay, so the hand is going to the left, friction's going to the right, and the normal force, in other words, like the resistance, the blockade from M1 is also going to the right. So they both get minus signs. So I say hand minus friction minus N1 equals M2A. I'm solving for N1. I don't know why I put the numbers in first. That was like a bad habit, but I'm solving for N1. I know everything else, including the acceleration, because every piece of the system is accelerating at the same rate, the one we found before, 0.75. So I do all the math, and lo and behold, oh lovely, I do get 3.75 newtons. The same answer as I got for before, as predicted by Newton's third law. So if this were exam, I would be like, yay, check, check, check. Like maybe I would write something like that, but also in my mind, I'd be like, cool, it's all coming together. It means I'm doing something right. Right, okay, so that's that. Now, there's a little bit more, there's a bonus part of this problem. It was like bonus. I mean, you didn't have to do it as far as homework points are concerned, but it's super helpful to warm us up or to shift our attention into the lab concerns. They throw an angle in the bonus, right? They say redo the whole problem, and we're on track here for time. It won't take us that long. They say redo the whole problem, but are now believing that the hand is pushing at an angle, pushing down 60 degrees below a horizontal. And please always, no matter how abstract these things are, whenever you're given an angle or you're thinking about an angle, the default assumption is angles are always measured from horizontals. And so whenever you're putting vectors together, tip to tail, whenever you're putting two legs of a right triangle together, or whenever you're resolving a hypotenuse into two legs, my huge pro tip strategy advice is always draw your horizontal first, and then from the tip of the horizontal, start the tail of the vertical. I think that's a real pro tip, because no one who doesn't practice this stuff will ever even know that there's any other options. They literally won't know what I'm talking about if you never practice these things. But if you practice making triangles and resolving vectors and stuff, you start realizing that you have choices about which vectors to draw first. And I'm telling you, the strategy for anybody who practices and is always draw the horizontal first, and then start a tail from the tip of the horizontal, and everything will work out cleanly. That is like, it's possibly my best pro tip ever, because it doesn't mean anything to anybody who isn't a pro. But anyway, okay, that's obnoxious. I'm going to go on. All right, so here, the new situation is that there's an angle now. Other than that, everything is the same. So we're redoing the problem. They ask for a system schema. The system scheme, I'm just like redoing parts A through B, right? I mean, through everything. System schema has got to be the same as before, because all we've changed is a direction of a force, and the system schema is manifestly not about direction. It's just about identifying the forces. So we haven't changed that. So the system schema is the same. Then it asks for the free body diagram, the pure free body diagram. Now something has changed there. The hand is no longer horizontal. The hand is at an angle. I'm just changing the view on the screen. So I change that in the pure free body diagram. Okay. Then I'm supposed to go on to part C and start answering like, what's the normal force and what's the acceleration? But now I have to pause, because yes, I want to go on to part C, but see, now I have a pure free body diagram that I can't work with. I mean, now I've got at least one vector that is not parallel or perpendicular to all the others. I have at least one. So now I have to pause and make a component diagram, right? I mean, in theory, I always have to have a component diagram. The reason I didn't have to make a new one up until this point is because I already had one. All the vectors were pointing along obvious axes. Now I've got to break something up. And here's it now, another sort of pro tip, or like foreshadow to the lab. it might seem obvious to you which vector to break up. And I don't disagree. If you're thinking I'm going to break up the hand vector, I mean, I agree with you. You're right. But let me tell you why. It's not because it's a diagonal line. This is what throws people off about the lab. There's no rule that says anytime you have a line that looks diagonal on the page, that's what you have to break up. No, sometimes we break up vertical or horizontal lines. The idea is that any vector or vectors that are not lying along one of our coordinate axes, any vector that's not lying along an axis has to be broken up, which means what we have to do consciously all the time is follow Galileo. We have to explicitly choose what are our axes. Like, are our axes looking like this? Or are our axes looking like this? Or this? Or this? Or are they polar coordinates or some other kind of coordinate system? Up until now, axes are not always horizontal and vertical. What is the strategy for now? Now, the physics will work no matter what your axes are. But some physics is a lot easier to do than others. Like, you'll get the same answer ultimately, but some things will cause a lot more work than others. What is the strategy that I've been saying that we've been following, but it doesn't feel like we've been doing anything, is always line up your positive x-axis to be aligned with, to be parallel with your positive acceleration expectation. Right? So I'm saying this on purpose because of the lab. The strategy is that wherever the thing is going to accelerate, you line up your x-axis with that. Now, in this case, in this problem, and in the sled problem, and every problem we've done to this point, the whole thing we expect to accelerate horizontally to the left. Okay, so here I'm going to say that my x-axis is to the left. Yes, just like we did that yesterday without even really thinking about it because we weren't breaking anything up. But I'm saying the key step, whenever you're going to, breaking up vectors can be tricky, especially, let's be honest, in the lab, you're breaking up MG. It's weird. Like, if it didn't throw you off for a minute when you first did it, then you're being dishonest. I mean, it throws most people off that we're breaking up MG. Most people don't know why, and most people don't know how. Certainly including me when I first did it. And then maybe people just sort of accept it and just chalk it up as one of those weird science things, and they just listen to the teacher and they go on. But then if they just do that, then actually finishing the lab report or ever doing inclined planes again is like a very dicey experience. What I'm trying to tell you now, before you look at MG in the lab, I'm saying that the strategy is you explicitly pick an x-axis to line up with the direction of acceleration, and then you make your y-axis perpendicular to that, like axes are always perpendicular. So I'm saying in this case, left horizontal is x, up is y, and then anything that is not, any vector arrow that's not lying along one of those axes is going to get broken up into two components that lie along those axes. Okay, so yes, in this case, the one vector to break up is the one that everybody would expect. It's the hand vector. Okay, so I zoom in on the hand vector. So here's the hand pointing down and left, right? Every vector is actually the hypotenuse of its own individual right triangle. So I draw the thing going down and to the left. And then if you practice this, you'll realize there's choices. Like, there's different ways I could turn that into a triangle. But if you follow the pro trip strategy, I started the tail of that vector that's going down and to the left, and I first go over to the left. I draw my horizontal first. Like, if you really think about it in practice, you could do it a different way, and you'll appreciate my way more when you try the different ways and see what happens. I go to the left. I draw a tip at the end of that leftward vector, and then from that tip, I make a tail that goes down. Tip plus tail makes result. Right? We're saying to go down and to the left is really to go somewhat down and go somewhat left. It's addition. Okay. And by the way, if this were an exam and you just did something like that, but you didn't have any tips or tails on it, and you just made like a triangle, I would take off points. I am obnoxious that way. These are vectors. This is physics. It's not just math. It's not just numbers. It's actual directions in space. So anyway, that's your triangle. You've zoomed in on the hand. And then on the hand force, which is 10 newtons at 60 degrees. So you get the two components of that force. The adjacent takes a cosine, cosine is adjacent over hypotenuse. The opposite takes a sine. So the horizontal component, how much the hand is pushing over, is 10 cosine 65 newtons. The vertical component is 10 sine 68.66 newtons. Okay. So now the purpose of why you zoomed, and by the way, if there were other vectors in this problem that also needed to be broken up, which is totally possible, to get back to the genius question of like, could there be more than one? There could be a million vectors. There could be a million vectors that are all off axis, and each one you would break up by this method. And then the purpose of why you're doing it is now the components, we're saying literally that the left plus the down equals the diagonal. So in our diagram, we're going to take out that diagonal because we can't do math on it. We can't do anything with it. And we're going to substitute in its place the two components that comprise it. It's like, if you can't deal with the number 5, deal with the number 3 plus 2 instead. Like, that's what we're doing. So we make a new diagram now, a component diagram, where every vector in the diagram is either going along the x-axis or along the y-axis. Like, and there happen, again, this is back to like sort of the genius question, and I'm not being, I mean, I'm being silly when I keep saying genius, but I'm not, but it does go back to that question. Like this diagram is getting complicated. There's 5 forces now, but all of them are along axes. That's the point, right? So now we have the normal, we have the friction, we have the weight, but what we've added is the cosine component of the hand and the sine component of the hand. And they are going, as we predicted, like to the left and down. Now, I didn't put the number, I tend, in my diagrams, I don't like putting numbers directly in my free body diagram. So I just rewrote it again as like hand cosine theta, just so you could see in general what I was doing. But of course, we know the numbers for those and we'll use them in a minute. So this is the diagram. Also notice though, like the hand cosine theta vector is still meant to be, hello. The hand vector is, I'm assuming, is longer than the F vector because the thing is going to accelerate to the left. And I'm assuming that the normal force is bigger than either of those two downward, like the normal force is not supporting the weight of this object anymore. The normal from the table, the upward normal force is not sufficiently supporting the weight of this whole system anymore. It's got to do more than that, because now someone's pushing down on the system as well, right? That affects the normal force. I believe now that normal end up, like that, the length of that arrow really should be like equal to the length of both of the downward arrows added together, which I don't know how accurate, like I did that, but something. Maybe you see my point. Anyway, that's my component free body diagram. You could do, some people will like go like that, or so. I mean, you can attach it however you can, make the drawing how you want. But I've now got 5 forces that are all going to go into F net equals MA, but I can now use them because now I can do F net equals MA on one axis at a time. And I'm first going to go to the y-axis because I was asked for the normal force, which is acting in the y-axis. So I say N up minus weight down, but also minus the hand sine theta thing down. All that together has to equal MA in the y-axis, and A in the y-axis is 0. So the normal force, I'm saying here, is doing more than, so this is like, this normal force is now doing the same kind of job as the normal force in the elevator with the duck. Like, it's for a different reason. Well, it's for what looks like a different reason, but it's ultimately the same thing. Someone's pushing down on the objects. So if the normal force just only supported the weight of the objects would crash through the table. The normal force is doing more than that. It's also supporting the downward effect of the hand. So the normal force has now gone up from, if bottom line, so it's gone up from 80 newtons to 88.7 newtons. Bottom line, if there were a scale on the table here underneath these double blocks, if there were a scale, the scale before would have registered 80 newtons. Now it would register 88.7 newtons. Like, it's just the same as the elevator effect. Okay, so that's the y-axis. And the x-axis, the cosine component of the hand minus the friction equals the MA. So we plug in the numbers, and we get a lower acceleration than before, which I think is not surprising, because the hand is still exerting the same amount of strength as before, but now only some of that strength is going into horizontal productivity. Like what the hand is doing, a lot of it is being wasted into vertical motion. And the truth of the matter is, by the hand pushing down, it's also increasing that normal force, as you see, which means really in reality, that would also increase the friction on the blocks. You weren't asked to take that into account in this problem because it was like assigned earlier, but really that would increase the friction. So definitely the acceleration of this whole thing to the left has gone down, should go down, and has gone down. Okay, so that's the answer to that. I mean, I think that, and that's as far as I'm going to go. You could still adjust the rest of the answers to the problem, but that's the kernel of it. The key thing that we're trying to get across here is how you deal with angles. And the key lesson, I'm going to move to the lab now. Okay. But the key lesson here is when it comes time to break up forces, the key first step you have to do to break up forces is you first have to consciously choose what your axes are. And the strategy, and you're going to break up everything along to line up with those axes. And the strategy is choose an x-axis that lines up with the expected direction of acceleration. That's a strategy. You don't have to do that. You could still get the right answer if you don't do that, but you're going to do a lot more work if you don't do that. So with the lab, now I'm going to get us going here. I'm looking at the time. We got, okay, plenty. We got 28 minutes. I'm going to talk a little bit, but definitely stop me. And I will also stop. Like, I want to make sure that whatever your questions or confusions are about this lab, I answer them. But like, so now we're in the lab. We have an inclined plane. We have a rough inclined plane. We have an object that's sent up the rough inclined plane, and then it comes down the inclined plane, right? So it's sent up. The rough inclined plane has some coefficient of friction that we don't know. We ultimately figure it out, I think, at the end of the lab. But the plane is rough, so it's got a coefficient of friction. Gravity, the acceleration due to free fall gravity is g, like always. The plane is inclined at some angle that's given as theta. And if the object was sent up, the object is sent up initially, so there's some initial velocity that sends it up. That's a known or a given. But so this is my step one. Like, this is the situation of the lab, and I'm just drawing it so that you now know when I draw any free body diagrams now or component diagrams, this shows you how they're oriented, right? Like they won't make any sense unless I'm picturing that my slide goes this way. Your slide might go the other way, but then all your diagrams should be oriented to that. Okay, so this is the situation as far as I see it. So if we look at the up trip, if we first just do a pure, I'm skipping system schemas for now. I'm assuming you already did that. You're fine with it. If I go to the pure free body diagram for the up trip, this is it right here. This is the pure free body diagram for the up trip. Notice a couple of things. Gravity's pulling down as always, mg. The normal force is going perpendicular to the plane of contact, right? One surface is pushing the other up into the left, in this case, because my plane is going like that. And if the object is on its way up, then friction opposes that and is going down along the plane. Friction and normal are perpendicular to each other, like as they always should be. Oh, hello, didn't mean to do that, sorry. Oh, we're going to get interrupted. Oh, no, we're not. Okay. Friction and normal are perpendicular to each other as they necessarily always are. Friction's along the plane. Normal is like from the plane, against the plane. Okay, that's my pure free body diagram. Now, clearly, something's got to get broken up here, because not everything is parallel or perpendicular. So we're good. Something's going to be broken up. But before I break anything up, let's just be clear that the pure free body diagram for the down trip is different, right? This is the pure free body diagram for the down trip. The track hasn't changed its orientation. The planet Earth has not changed its orientation. So mg and the normal are still the same, but if the object is on its way down now friction flips and is pointing up, and that's going to make all the difference. That's the key thing in this whole lab. I think from up to down, the magnitude of friction is going to be the same. The magnitude of the normal is going to be the same. The magnitude of the weight is going to be the same. The key to the whole lab is the fact that the direction of friction will flip from up to down Oh, and by the way, notice in the up trip, there is no upward pointing force, no, right? These two diagrams are the same, except for the direction of friction. V naught is how the object originally gets going, but V naught is a V. It's not an A, and it is certainly not an F. So V naught does not go in your diagram. And especially because the diagram is what's going on at any instant during the lab, like once the stopwatch has started, once the object, oh, here comes a possible interruption, but once the object has already gotten going and is moving up the plane, but accelerating down the plane. I'm going to say this one more time. Velocity is not a force. Motion is not a force. Diagrams are of forces. So, and put another way, you flicked the object initially to get it going, but you're not touching it anymore during the progress of this experiment. So this is the pure free body diagram of the up trip. This is the pure free body diagram for the down trip. Oh, yes, Chris is right. He will be coming right at the crucial moment, of course. If he says no homework, actually, by the way, you still have no homework because you're working on whatever. You just don't. Maybe I'll tell him it's because of him. Anyway, all right, now we got 24 minutes, which should be plenty. The key thing now is, in order to do any analysis at all, to figure out acceleration, especially to compare acceleration up to acceleration down, in order to then compare time up to time down, which is the whole point of the lab, we must do F net equals ma on each axis, which means we need all of the force vectors to be lying only along the axes. We don't have that here. We clearly have vectors that are going in not parallel or perpendicular to each other, okay? Now, if we were just blindly following unconscious habits and just thinking, if we were just thinking, oh, every time you see a diagonal line, you should break it, you should treat it as that. If we just thought that diagonal lines were hypotenuses of triangles and that they have to be broken up into legs, it would be very easy to think that we should break up the friction or the normal, right? Because they're diagonal lines. Or if we've gotten used to the idea that gravity pulls straight down and straight down seems like it's along the y-axis, we might well think, as I certainly did in college when I first saw this, I would think, well, mg is fine, let's not mess with that, but I guess we've got to break up friction or the normal or something. If we break up friction, we also definitely have to break up the normal and vice versa. If we want to leave gravity alone, we'd have to break up two forces. That's number one. But let me also say, and I'm not saying you couldn't do that. In fact, it's often a problem on the final exam to see what happens when you do that. We'll talk about that. I'm not saying you can't, but if you want to leave gravity alone, first of all, you'd have to break up two forces, normal and friction. So that's twice as many sines and cosines as you'd have to deal with. But then, let's be really clear. Then, if you do that, you're saying this is your x-axis and this is your y-axis. And if you say that this is your x-axis and this is your y-axis, then the fact that the object is accelerating along a diagonal line means that the acceleration will have a cosine component and a sine component. Like, you really want you to think about that. I'm saying if you leave gravity alone, you can, but you'd have to break up friction and normal, and you'd have to break up acceleration into sine and cosine components. So you'd have 3 times as many sines and cosines to deal with if you leave gravity alone. The physics still works out, but it is a lot longer and a lot more room for error. I mean, and so this is the beauty of physics, that physics works in all coordinate systems. It does. But therefore, we make strategic choices as to which coordinate systems will save us the most hassle. So we follow the pro tip strategy that I've been saying for all the other problems, but just didn't seem like anything interesting in the other problems. We say, wait a second, let's line up our x-axis with the acceleration so that along one line, the acceleration doesn't have sines or cosines, it's just the acceleration. And even better, along the other axis, the acceleration will be 0. Which is a number that's so easy to work with, or makes our life even doubly better. Here he is, ladies and gentlemen. Okay, there he is. There, looking happy as usual. Hello, how are you? We're about to.
You said 4 minutes.
Okay, guess what? In honor of Felix's presence today, I'm actually. Oh, they say hello. They're saying.
Everybody say happy birthday to Dan.
Oh. Wow.
Everybody say happy birthday to Dan.
Oh well, they're on.
Now.
Happy birthday.
Oh, what? Thank you. Oh my God. Okay.
Good.
Wow. Oh, that.
Everybody else do it, or else you have double the
No,
homework.
you can't say that. But no, you can't threaten them. It was nice of you to say, but they actually are not getting homework tonight because I was just about to. But thank
You
you.
will get homework
No,
if you
all right,
don't
no, you
say.
can't threaten. Okay, thank you. Oh, who's Dan? They said, who's Dan? That's funny. That's me.
Yeah,
Okay.
that counts.
All right,
Now,
all right, thank you. They wrote it. Thank you both.
Wait, it's your birthday?
Well, actually, it's tomorrow. Okay, thank you. Guys. That was very sweet in
yes,
both.
it is tomorrow.
I can't believe that might be the first time. Thank you, Felix, for remembering. It is tomorrow, actually. Okay. Who's Dan? That's funny too. And they did say hi, Felix. Okay. Thank you all. That was very sweet. And yes, you don't have homework either way. Wow. Thank you guys. Okay. Yes, it is my, okay. Can you believe I'm 32? Just kidding. Okay. Yeah, Scorpio season, absolutely. And I'm 53. I'm still of an age where I don't mind saying that. Okay. Wait. Okay. We're still okay. It's still okay at time. I budgeted that in this time. I did budget that in. Okay. But no, that's very nice. Work for him. He does have, oh my God, don't even get me started. Wow, that's really nice of all you guys. Holy smokes. I actually cannot believe he just remembered that. Okay, anyway, Dan, happy birthday to. Okay. What I'm saying now is that if we line up our X, see, this is what I think that, frankly, I think this always gets skipped in the lab. I don't think people realize this is what, I know you've been in the lab, and I know you're seeing that people are breaking up MG into MG sine and cosine, but like, I think some of you are legitimately confused by, I'm guessing, some people are legitimately confused, and some people have just accepted it and are moving on, and they're not even letting themselves be confused by it, but you should stop and think about, why the heck is MG getting broken up? Isn't that weird? Because what we're saying is we're lining up our x-axis to match the direction of the acceleration. Like this object is accelerating along a slide, right? Along an incline. So if we tilt our head and make the x-axis line up with that, that is huge advantages. One, it means we only have to break up one thing now. We will have to break up gravity, which is a little weird, but we won't have to break up friction. We won't have to bring up normal, and we won't have to bring up the acceleration, break up the acceleration. And it means that if we say it's accelerating all along the x-axis, then we have this advantage along the y-axis. We could say the acceleration is 0, so we can balance forces. You can't say that forces are balanced unless the acceleration is 0. So it gives us, so this is the strategy we always do in physics. We try to line up the x-axis with the acceleration. It vastly simplifies calculations. And if we do that, so if we tilt our coordinate system, make the x-axis go down, like, and by the way, also, I don't care whether this thing is moving up or moving down, it's accelerating down either way, right? Just like when you throw something up, it slows down on the way up, it speeds up on the way down, it's accelerating down either way. So I make down my positive x-axis. Then, therefore, gravity, the vertical line of gravity is no longer along a y or an x-axis. It's bad. It's a hypotenuse of its own right triangle. So I zoom in on gravity, right? And this is the weird part, but no one ever, people, you have to get used to the fact that hypotenuses can be non-diagonal. You get it. So gravity is the hypotenuse. We're dividing it into two components, a sine and a cosine component. Sine is opposite the angle, cosine is adjacent to the angle. What we're saying in English is that if gravity, of course, gravity is just still pulling the object straight down. But because the object is on a plane, that means gravity is having two distinct effects. These two different force components are not just raw math. They're physically saying something. They're saying that gravity is doing two jobs once we've introduced a plane. In other words, the weight of the object is contributing two effects to this phenomenon. Some portion of the weight, the sine portion, is sending the object along the plane. The other portion of the weight is keeping the object on the plane. It's pulling it into the plane, right? Right? Both things are happening. The object is staying on the plane. It's not like flying off it or crashing into it, but it's also gliding along it. So the gliding along is the sine component, and the other one is the cosine component. Where did I get that from? I got like, and that's the tricky part of this. And I do, depending on what your questions are. So, okay, so the first thing I'm acknowledging is what I think is tricky or worth thinking about in this lab is like, why did we break up gravity? I hope I just explained that. But then the second question is, all right, if we are breaking up gravity, how do you know which one is sine and which one is cosine? That's a very fair question. And I could talk a lot about that, but I'm going to try to do it in layers. My first answer is, well, the sine is always opposite from the angle. Cosine is always adjacent to the angle. The angle is right there. Now, wait a minute. How do I know? Like, why did I know? So the next question is, what do I mean the angle is right there? Like, why didn't I look at the other angle? The angle that's given in the problem, the angle that you know in the problem that we called theta, that you measure in the lab, is this angle down here, right? That's the angle you know. So when we tilt the triangle up on its, when we tilt gravity up on its side, the question in the right triangle that I made, the question is, which of the two angles in the new triangle is congruent, is just a different way of looking at this same angle. In other words, I don't want this. This is something else, call it fierce. I don't want that in my new triangle. I want to label in my new triangle whatever is equal to this one down here. Now my claim is that this one down here is that one over there. How do I know? Well, one thing is just tilt it on its side. I mean, if you, I'm so stupid. I just tilted my tablet on its side as though that would happen on your screen. Wait, actually, wouldn't it though? Wait. Yeah, oh, well, okay, there goes that. If you tilt your head to the side, then you see the inclined plane making an angle with the horizontal, right? That, like, the angle of the plane making it with the horizontal is what we have labeled in the original picture. So one thing I'm just saying is that's this angle down here. It's not the other one. The other one is the complement of this. This is the original angle. There's other things I could say too. You could like do a whole bunch of geometry and draw lines and see, like, you know, like when two parallel lines are cut by a transversal, the alternate interior angles are congruent. You can do stuff like that and satisfy yourself. But I think if you just tilt the page, you'll see. But also, how can I put this? Well, I'll say this once quickly. The other real way to see why the component of gravity along the plane is sine and the other one is cosine is that if you really think about it, and this is the test we always do, if you really think about it, just put it this way. If there was no angle at all, if this were horizontal, then gravity would not be sending the object along the plane at all, right? Gravity would be 100% pulling it into the plane. If the plane were horizontal, gravity would not be sending the object along the plane, right? Like, in other words, this is like the sliding axis. Gravity would not be sending the object along the sliding axis at all if the plane were flat. Who cares? Why am I saying that? Because if the plane were flat, the angle would be 0. And the sine of 0 is 0. So what I'm actually arguing, and I'm going to move on a second and basically just get questions from you, hopefully, but I'm saying if you ever, this is a big thing in physics, if you get to the point of knowing what you have to break up in any physics problem, and it doesn't go away in physics 204, if you have a vector and you know you got to break it up into components, and your issue is, if you're good enough to be down to the common physics confusion of which one is sine and which one is cosine, first of all, congratulate yourself. If that is your issue, if you are stressed or confused about, I understand everything, but I don't know which one is sine, which one's cosine, then join the physics club. Like, that is like good. Like, that's what physicists care about. Which one is sine, which one is cosine, means you're in it to win it. You're with us. But how do you resolve this? Actually, the trick is always to remember sine of 0 is 0. Sine of 0 is 0. So whichever one would disappear, whichever force wouldn't be there, in the zero case gets the sign. And whichever, do you see what it takes some getting used to, but I'm hoping at least two of you that it just clicked what I just said. And I'll say it again another way, another time. But anyway, and I see there's things happening in the chat, which is great. And we still have 10 minutes. I'm just going to take what I'm saying now is we now take the sine and cosine component and we substitute them into our diagram. I am going to look in the chat in 1 second, but right, like instead of mg, I now put mg sine theta going along the same axis as friction, and I put mg cosine theta going in the same axis as the normal force, both in my up picture and my down picture. And right, so now I have component diagrams for up and down, and and both of them are ready to go and do Newton's second law on. The big difference is that in one case, friction's helping gravity sine theta, and in the other case, friction is opposing gravity sine theta. By the way, I don't mean to imply one thing, and then I'm going to look in the chat. I don't mean to imply at all that they're the same length. I assume that actually gravity is a lot longer than friction. I don't mean to imply that they're the same length. But I do mean to imply that friction is always the same length, whether it's up or down, and mg sine theta is always the same length, whether they're up or down. And I do mean to imply, like here, these are equal because the acceleration, because a sub y is 0. So the n must be equal to the mg cos theta. That's why we chose our coordinate system this way. But in okay, I'm gonna so wait, hold on a second. I'm just gonna write this and then I'm totally gonna chat. So up we have mg sine theta plus friction equals ma, and down mg sine theta minus friction equals ma, and that makes all the difference in the discrepancy between the times of the two, and all the difference as to why you get the surprising result that it should take more time to go down, right? It's slower on its way down. That's the punchline of the lab. But if you really think about this, it actually explains it. But wait, and I'll say more, but I'm glad things are having their chat. Oh, okay. Yeah, unit circle. Yeah, for real. Yes, it's totally all about the units. It's all about the unit circle. It is. Yes. So wait, I could say more. Believe me, I could, I could say more, but I do want to make sure I want to pause. There's 7 minutes left and I don't want to go early, but are there any, please ask me questions about this lab that I could help you with.
Can you go back to the page
yeah,
before
absolutely.
for a second, please?
Yeah, absolutely.
Thank you.
No problem. So I could still go farther, but are there any, is this, I'm going to.
What's the arrow? I'm sorry.
No, please say.
What's the arrow that's like unlabeled in the down? Is that the friction?
Oh, sorry. Yes, it is. Good point. Yes, it is. I don't know how I got unlabeled. Yes. Good point.
Thank you.
Yeah, thank you. Okay, so good question. So I'm going to slowly keep talking, but really, I'll feel better if other people besides Melita or Chris interrupt me or say anything that's concerning them about this. Because I think this is not easy. I think it's really important. I think it's one of our cooler labs in many ways. And I think, here we have the luxury of we're right in sync, the lecture material with the lab material. So it's really an opportunity for you to stop me. I'm going to talk for 6 minutes if you don't, but I will stop on a dime if anybody does. See what I'm saying here now. Well, first of all, we could go one more step, right? If we look okay, so this is true. If we look at the y-axis, if we look at the way we've set this up, if we look at the y-axis, then n minus mg cosine theta equals ma in the y-axis. But in the y-axis, the acceleration is 0 because of the way we set this up. Again, if you didn't break up gravity, we couldn't do what I'm doing right now. But because we break up gravity, we could say n equals mg cos theta. So that's a way of saying, the track supports some of the weight of the object, but not all of the weight. And the rest of the weight sends the object down the plane, right? remember, friction is mu times the normal. So we can substitute in, we could say on the way up, mg sine theta plus mu mg cos theta equals ma, and then all the m's will cancel out if you like. And on the way down, mg sine theta minus mu mg cos theta equals ma. But here, right, and then you can start putting in numbers, but here's the key, the real key point is this plus versus this minus. Like the punchline of the lab is that the object takes more time to go down than it does. I mean, I hope most of you found that, or at least ultimately found that most people found that, right? Like if you set this up nicely and you're careful and your angle is small and all of that, you find that the object zooms up the plane and then dribbles its way down. And this is just a realistic, this is just like a pushing something up, like there's no tricks. This isn't like a specialized circumstance. So what we're finding is that on a regular, realistic, rough inclined plane, things take longer to come down than they do to go up. They're slower on the way down than they are on the way up. I mean, I would think that's a slight surprise to some of us. But it's true. Why? Because on the way up, gravity is helping friction, right? When the ball is on the way up, now, by the way, notice, I mean, that's a plus sign. Notice the positive direction for all of this is down. Like I didn't change my coordinate system from one situation to the other. So I'll just leave it at that. But so when you're on the way up, the two forces, gravity and friction, yeah, they're both pointing down. So it seems like everything's against you when you're moving on the way up. But all the forces are helping each other. Gravity and friction are both helping each other slow you down. So you think, well, that's bad if they're both slowing me down. But when are you going to be done on your way up? You're going to be done when you've fully run out of speed, right? The object goes until it runs out of speed. So everything is working to slow the object down as quickly as possible. So on the way up, the object loses speed super quickly. The net for all the forces are working together against it. So the net force is huge. Like just plug in numbers. Like imagine that this number is 7 and then therefore this number is 7. And imagine this number is 3 and this number is 3, right? Because the numbers don't change. It's just a question of that one sign that changes. So on the way up, you have like a net force of like 10. And you divide by your mass, so you have an acceleration of like, say your mass is 2, so you have an acceleration of like 5. That is a downward pointing acceleration. That's the rate at which you are losing speed. But losing speed is a good thing when you're on your way up, because as soon as you're done with it, you're done with the up trip. Now you start coming back down. Now gravity is helping you down, but friction's going against you. So gravity and friction are not helping each other anymore. It's now no longer a sum, it's a difference. Like the net force on you on the way down is not 4 now or something rather than 10, just to make up numbers. So you divide by the mass. And so now So now your acceleration on the way down is like 2. Now, granted, that's in the direction that you're speeding up on the way down, but you're speeding up at you're gaining speed on the way down at a much lower rate than you lost speed on the way up. That's the surprise, right? So you lose speed really quickly and you run out of speed at 0 and you get to the top, and then you dribble back your speed. You gain your speed in a dribbly way on the way back down. And in fact, if you really think this all through, you never gain back all the speed that you started with. That's how asymmetric it is, right? Like if you started with an initial velocity of 20 meters per second, you go 20 up to 0. And then you come from 0 down and you only gain back some of your speed in the same distance. So you end up with a final speed of like 16 or something. So your average speed on the way up is literally faster than your average speed on the way down, because your acceleration magnitude on the way up is literally higher than your acceleration magnitude on the way down, because the net force on you on the way up is literally higher than the net force on you on the way down, because on the way up, the forces are acting together, and on the way down, they're acting in conflict. That's the whole difference. But you can't see that until you break everything up into components, as we did. I don't know if that, hopefully that helped somebody somewhere with the lab. I don't know. Like, if I were grading your lab reports, like, I'd want to hear that explanation in it. Like, that's what I'd be looking for. But obviously I'm not Mercedes, blah, blah, blah. But okay, hopefully that was helpful. Happy birthday. So I'll hang out and answer any questions. But other than that, there's no new homework because why? I don't know. So have a great weekend and I'll see you Monday. But I'll hang out for questions. But I'm turning off the recording. But yeah, enjoy my party. Thank you. Oh, good. Oh, thank you for saying. Oh, good. Oh, great. I'm glad if that lecture helped. Great. Thank you. Now I will have a good birthday because if you have good lab reports, I will have a good. Thank you. Yes, and go Scorpio. Okay, I'm turning off the.